What if space isn't empty? And I don't just mean it has planets and stars and gas clouds in it. I mean the space itself, the background, the thing we move through. What if that's not nothing? What if it's a something? This is an old idea in a way. For a long time, scientists believed in something called the luminiferous aether. It was supposed to be a substance invisible and everywhere that light waves traveled through. Like sound travels through air, light was supposed to travel through the aether. It made a certain kind of sense. But experiments in the late 1800s, most famously by Michelson and Morley, failed to find any evidence of it. So science threw it out. Then Einstein came along. He gave us a new picture of space. He joined it with time, creating spacetime. And he said the spacetime wasn't just a static stage for events to happen on. It was a dynamic, flexible fabric. Massive objects, like the sun, don't pull the Earth with a mysterious force. They bend the fabric of spacetime, and the Earth is just rolling along the curve. Gravity is geometry. This was a huge leap. Spacetime became a real physical thing. But it was still a classical thing. A smooth, continuous sheet. Then came the other revolution. Quantum mechanics. Quantum mechanics tells us the world is not smooth, it's jittery. It's grainy. It's made of tiny, discrete packets of energy called quanta, and it's deeply weird. Particles can be in multiple places at once. The act of looking at something changes it. And a vacuum, a truly empty space, is not empty at all. It's a bubbling, frothing sea of virtual particles that pop into existence and disappear in an instant. This is called the quantum vacuum. For 100 years, these two great theories, general relativity and quantum mechanics, have been the pillars of physics. And for 100 years, they have refused to work together. Relativity describes the big things, the smooth curve of space-time. Quantum mechanics describes the small things, the jittery dance of particles. When you try to use them together, like to describe the inside of a black hole or the first moment of the universe, the math breaks down. You get infinities, nonsense. This is the biggest problem in physics, finding a theory of quantum gravity that can unite the two. And this brings us back to our question. What is space? Is it the smooth fabric of Einstein? Or is it the bubbling quantum foam? A small but persistent group of physicists thinks it might be something else. Something that looks like Einstein's fabric from far away, but is made of quantum stuff up close. They think space itself might be a liquid. And not just any liquid. A very special kind of liquid. This is a superfluid. To understand this idea, we first need to get a handle on what a superfluid is. It's one of the strangest states of matter we've ever discovered. Think about a normal fluid, like water or honey. If you stir it, it swirls for a bit and then stops. It has friction, both within itself and against the container. This internal friction is called viscosity. Honey has high viscosity, water has low viscosity. But they both have it. Now imagine a fluid with zero viscosity. Absolutely none. If you were to stir it, it would just keep spinning. Forever. It would never stop. This is a superfluid. We've actually made these in labs. The most famous example is helium. If you cool helium down to just a couple of degrees above absolute zero, it undergoes a phase transition. It turns into a superfluid, and it does some truly bizarre things. If you put it in an open container, it will creep up the inside walls, over the lip, and down the outside, seemingly defying gravity. It does this because with no friction, it can spread out into a microscopically thin film that covers every available surface. If you try to spin a bucket of it, the bucket will spin, but the liquid inside will remain perfectly still. It refuses to rotate as a whole, but if you spin it fast enough, something amazing happens. The superfluid will suddenly form tiny, perfect whirlpools, little tornadoes called quantized vortices. And it won't form just any old vortex. The rotation can only exist in these discrete, identical units. It's quantum weirdness, but on a scale you can see. So what's going on here? Why does it act this way? It's a state of matter called the Bose-Einstein condensate, or BEC. In the normal world, every atom is its own little individual, bouncing around and doing its own thing. But when you cool certain types of atoms down to extreme temperatures, their quantum nature takes over. The individual atoms lose their identity. They stop acting like separate particles and start acting like one single massive quantum object. They all fall into the exact same quantum state, overlapping and behaving in perfect unison. Imagine a crowd of people all milling about randomly. That's a normal gas. Now imagine they all start marching perfectly in step, thinking the same thoughts, moving as one. That's a Bose-Einstein condensate. This collective, coherent behavior is what gives a superfluid its strange properties. The zero viscosity, the wall climbing, the quantized vortices, it all comes from the fact that you're not dealing with individual atoms anymore. You're dealing with one giant superatom. Okay, so we have this weird form of matter. Say a liquid with no friction made of atoms that have lost their individuality and act as one. Now for the leap. What if the vacuum of space is a Bose-Einstein condensate? What if space-time itself is a superfluid? This is the core of the superfluid vacuum theory, sometimes called the superfluid space-time theory. It's an attempt to find a new foundation for physics. It says that the reality we see, the smooth spacetime of Einstein, the particles of the standard model, is not the fundamental layer. It's an emergent phenomenon. It arises from the collective behavior of a much deeper hidden reality. Think of it like the water in a lake. From a distance, the surface of the lake looks smooth and continuous. It's a two-dimensional surface. You can have waves and ripples on it. But if you look very closely, you see it's made of a huge number of individual, discrete water molecules all jiggling around. The smooth surface is an emergent property of the collective behavior of the molecules. The superfluid vacuum idea says something similar about spacetime. The smooth, continuous spacetime of general relativity is like the surface of the lake. It's what we see and interact with, but at a fundamental microscopic level, a level far smaller than any atom spacetime is made of some kind of basic quantum atoms. Let's call them space atoms for now, though physicists have other names for them. And the theory goes that these fundamental constituents of reality are in a Bose-Einstein condensate state. They've condensed into a single vast quantum object, a superfluid that fills the entire universe. What we call the vacuum is this superfluid. This sounds like science fiction, but the physicists working on it believe it could solve some of the deepest mysteries we face. Let's start with the big one, the clash between general relativity and quantum mechanics. Relativity is a classical theory. It's about smooth fields and curved geometry. Quantum mechanics is, well, quantum. It's about discrete packets and probabilities. The superfluid model provides a potential bridge. In this view, spacetime isn't fundamentally smooth. It's a liquid made of tiny parts. Gravity, the curvature of spacetime, wouldn't be a fundamental feature of reality. It would be more like the way a fluid flows. The equations that describe fluid dynamics, like the Navier-Stokes equations, can look a lot like Einstein's equations of general relativity under certain conditions. So gravity could be an emergent phenomenon. It's not a basic force of nature, but a description of the collective motion of the underlying space atoms of the superfluid. And the particles we see, like electrons and photons, they might not be fundamental either. They could be excitations in the fluid, like phonons, which are sound waves in a liquid. A photon could be a ripple in the superfluid spacetime. An electron could be a different kind of disturbance. This offers a way out of the conflict. General relativity would be the large-scale hydrodynamic description of the fluid. Quantum mechanics would be the description of the fluid's tiny constituent parts and their excitations. They would be two different descriptions of the same underlying substance, valid at different scales. That's the big prize, a unified picture. But the theory also makes some surprising claims about other cosmological puzzles, namely dark matter and dark energy. Let's talk about dark matter. When astronomers look at galaxies, they see something strange. The stars on the outer edges of spiral galaxies are moving way too fast. Based on all the visible matter we can see, stars, gas, dust, the gravity should be much weaker out there. Those stars should be flying off into space. But they aren't. They're held in orbit. The mainstream explanation is that there's a huge invisible halo of some kind of mysterious dark matter surrounding every galaxy. This matter doesn't interact with light, so we can't see it. But it has gravity, and it's this extra gravity that's holding the galaxies together. We've been searching for dark matter particles for decades, with giant experiments deep underground, but we haven't found a single one. We know it's there from its gravitational effects, but we have no idea what it is. It makes up about 27% of the universe. Normal matter, the stuff we're made of, is only about 5%. The superfluid vacuum theory offers a different explanation. It says there might be no dark matter particles at all. Instead, the effect we call dark matter could be a result of the spacetime superfluid itself. Remember how superfluid can have waves and ripples like the phonons of a sound wave? Well, tiny density fluctuations in the superfluid vacuum could create gravitational effects. These slight variations in the density of the background fluid would bend spacetime just a little bit extra. From our perspective, it would look exactly like there's extra mass there. Some models show that these superfluid density variations would naturally clump around massive objects like galaxies. They would form a halo, just like the dark matter halos we observe, so the missing mass isn't a new type of particle. It's a property of the fabric of space itself. Its space being slightly thicker, or denser in some places than others. This is a radical idea. It means we're not looking for a lost particle, we're looking at a feature of the stage on which everything is playing out. And what about dark energy? This is maybe even stranger than dark matter. In the late 1990s, astronomers discovered that the expansion of the universe is not slowing down, as everyone expected it would due to gravity. It's speeding up. Some mysterious force is pushing everything apart faster and faster. We call this force dark energy, and we have even less of an idea what it is than dark matter. It seems to be a property of space itself. Every cubic meter of empty space seems to contain a tiny, but non-zero, amount of this repulsive energy. It makes up the remaining 68% of the energy density of the universe. It's the dominant component of reality, and it's a complete mystery. In physics, this is often linked to something called the cosmological constant, a term Einstein added to his equations and later called his biggest blunder, though it turns out he might have been right. It represents an intrinsic energy of the vacuum. The superfluid vacuum theory has a natural place for this. Any fluid, even a quantum one, has a certain amount of internal pressure and energy density. The theory suggests that the energy of the superfluid vacuum itself could be the cosmological constant. The accelerated expansion of the universe wouldn't be caused by some mysterious add-on. It would be the natural consequence of the fact that space itself has a small positive pressure. The liquid of spacetime is pushing itself apart. So, this one idea, that space is a superfluid, could potentially explain gravity as an emergent phenomenon, replace dark matter with density fluctuations, and identify dark energy as the fluid's own internal pressure. It offers a unified physical picture of the cosmos that feels almost intuitive. Space is a substance, it can flow, it can have ripples, it has pressure. It even offers a new way to think about black holes. In general relativity, a black hole contains a singularity, a point of zero volume and infinite density, where the laws of physics break down completely. This has always been a red flag for physicists. Infinities usually mean your theory is missing something. In the superfluid model, a black hole might not have a singularity at all. It could be more like a vortex, and like the quantized vortices that form in spinning superfluid helium, but on a cosmic scale. Imagine the superfluid spacetime is flowing. An object like a star or planet is just a disturbance in that flow. What if a black hole is a place where the superfluid is flowing inward, like water going down a drain? The event horizon, the point of no return, would be the point where the speed of the inward flowing space fluid exceeds the speed of light. Since everything, including light, is just a ripple in the fluid, if the fluid itself is moving faster than the ripple can travel, the ripple can never escape. Inside the event horizon, there's no need for an infinitely dense point. There's just a very extreme state of the quantum fluid. It avoids the singularity and provides a physical description of what might be happening inside a black hole. So, if this idea is so great, why isn't it mainstream? Why isn't everyone working on it? Well, it has some very big challenges. The biggest one goes right back to the beginning, to the idea of the aether. The reason the aether was discarded was because of the principle of relativity. It states that the laws of physics are the same for all observers who are moving at a constant velocity. There is no absolute rest frame. If you're on a perfectly smooth train, you can't do an experiment to tell if you're moving or standing still. The speed of light, in particular, is constant for everyone, no matter how fast they're moving. Or a fluid or an aether seems to violate this. A fluid defines a rest frame. If you're moving through a fluid, you should feel a wind. You should be able to measure your speed relative to the fluid. This was the whole point of the Michelson-Morley experiment, to detect the aether wind as the Earth moved through it. They found nothing. So, how can a superfluid vacuum be compatible with 100 years of relativity being proven right again and again? Proponents of the theory have a clever answer. They argue that the Lorentz invariance, more the principle that the laws of physics don't change for different observers, isn't a fundamental law of nature. Instead, it's an emergent property of the superfluid at low energies. Think about it like this. Sound waves travel through air. The laws governing sound waves are not Lorentz invariant. There is a clear rest frame in the air itself, but what if there was a world of creatures that were themselves made of sound waves? They could only interact with each other via sound. For them, the speed of sound would seem to be a fundamental constant speed limit. They might not even be aware of the underlying air. Their physics would look to them to be perfectly relativistic. The idea is that we are like those sound wave creatures. And all the particles we're made of are just excitations within the superfluid. So we can't perceive our motion through the superfluid. For us, the speed of light, which is the maximum speed of ripples in the fluid, appears constant. The relativistic rules we observe are a consequence of the fluid's low energy behavior. However, the theory predicts that at extremely high energies, this symmetry might break. If you could create a particle with enough energy, you might be able to see the underlying graininess of the superfluid. You might see that the speed of light isn't perfectly constant, but these energies are far beyond anything we can reach in our particle accelerators. So, it's a prediction that's very hard to test, and that's the other major problem, a lack of clear, testable predictions that distinguish it from the standard models. The theory is very good at post-diction. It can be tweaked to explain things we've already observed, like galaxy rotation curves or cosmic acceleration. But coming up with a unique smoking gun prediction that could be tested tomorrow is much harder. Science advances by falsification. A good theory makes bold predictions about things we haven't seen yet. If we go look and find them, the theory gets stronger. If we don't, the theory is wrong. The superfluid vacuum theory is still in a stage where it's more of a framework, an alternative way of looking at things, than a fully fledged predictive theory. There are other technical challenges too. How do all the different particles of the standard model electrons, quarks, neutrinos, Higgs bosons arise as different excitations of a single fluid? Getting this to work out mathematically is incredibly complex. While the basic idea is simple, the details are formidable. So, where does this leave us? Is space a superfluid? The honest answer is, we don't know. It's a speculative idea. It's not part of mainstream physics in the same way that string theory or loop quantum gravity are. Those are the big, well-established research programs for quantum gravity. Superfluid vacuum theory is more of an underdog. But it's an idea that refuses to go away because it's so compelling. It speaks to a deep human intuition that space shouldn't be nothing. It should be something. It gives a physical, almost mechanical picture of the universe. Gravity is fluid flow, particles are ripples, dark matter is density changes, dark energy is pressure. It all fits together in a neat conceptual package. It reminds us that our most fundamental concepts are up for grabs. We think of empty space as the most basic, simple thing there is, but maybe it's the most complex and important thing in the universe. A vast, hidden ocean of quantum reality whose properties dictate everything we see. The history of science is full of these kinds of shifts in perspective. We once thought the Earth was the center of everything. We once thought time was absolute. We once thought matter was solid and continuous. Each of these ideas seemed like common sense until a new theory showed a deeper reality. Maybe our current view of space as an empty, passive void is just another one of those common sense ideas waiting to be overturned. The search for a theory of everything is a search for the fundamental constituents of reality. For a long time, we've thought of this as a search for the smallest possible particle, the ultimate atom of matter. But what if the most fundamental thing isn't a particle at all? Like, what if it's a collective, a substance? What if the universe is not built from tiny bricks, but is carved from a single universe-spanning quantum fluid? We may never be able to directly see this superfluid any more than a fish can see the water it swims in. But by observing the universe, by studying its large-scale structure and its high-energy behavior, we might be able to infer its properties. We might see the subtle signs that tell us we are not moving through a void, but through a medium with a life of its own. For now, it remains a tantalizing possibility, a different path through the woods of modern physics. It could be a dead end, or it could be leading us toward a completely new understanding of what the universe is made of. The final answer is not yet written. The search continues, and the question remains. Is the stage itself the main actor? Is space a thing? Is it a fluid, and does it flow?